And today we'd like to talk about manifolds, meshes, and geometric graphs. So this is maybe a little bit more exotic. I think in most computer science programs, you usually don't encounter manifolds. So we'll try to convince you that these are interesting objects and they are worthwhile to be known and to be studied. So this was just a reminder for you. What kind of domains we considered so far. So we talked about the 5G of geometric deep learning, and today we're talking the last G. So we're talking about manifolds, meshes, and geometric graphs. And Taco after me will be talking about gauges, which is a generalization for manifolds, so what is called bundles. So I remind you also that we could define different popular architectures as instances of the geometric deep learning blueprint by choosing the domain and the symmetry group. And for example, in convolutional neural networks, the domain was a grid, and the symmetry group was the translation group. For example, we talked about graph neural networks, right, or deep sets, where the domain was a graph or a set, and the symmetry group was permutation. So here we are talking about intrinsic or mesh CNNs. The domain will be some discretization of a manifold, typically a mesh or maybe a geometric graph. And we'll see that we actually have two different types of symmetries or invariances. One of them is global. So we're talking about isometries with respect to some deformations. And another one will be local. So this will be what Taco then will expand on. We'll be calling gauge symmetries. So maybe first of all, why at all manifolds are interesting. So these are, as I said, a little bit exotic of an object in machine learning. So when we deal with problems in computer vision and computer graphics, we are trying to describe three-dimensional objects. So three-dimensional objects, in many cases, you can describe them as volumes, right? As shown on the left here. So basically, instead of pixels, you have voxels. And in this case, if you're not interested in what happens inside the object, if you're interested just in the outside, there is some disturbance. Maybe you can turn off your audio. Then we can model it. Sorry, Benjamin, I think. Yeah, thank you. So an alternative to modeling the volumetric representation of the object, we can think of a two-dimensional surface, the boundary surface of the object. And this is a two-dimensional manifold, right, that is typically discretized as a mesh. And as a result, we have significantly less wasteful representation. So when we are talking about deformable objects, like the human body, for example, or facial expressions, so then we can use techniques from differential geometry that allows very naturally to think of deformations and describe deformations of manifolds. Now, in other applications that we will also see in our guest talk, when modeling proteins, so proteins are large molecules that interact with each other and with other molecules in our body. And the way that they interact, they present to the outside world what is called the molecular surface. So we don't really care about, to a large extent at least, what happens inside, how intricately the protein is folded. So a way to abstract out this internal folding is to represent them as surfaces. And again, because they change their conformation when they interact, it is important to be able to treat these objects appropriately. So the two types of invariance that I mentioned, as we'll see, so if we have a manifold, we'll need to work with it locally. So first type of invariance will be the ambiguity in the change of or in the choice of the local system of coordinates. That's what we'll call the gauge. The second type of symmetry is global. It's a deformation. For example, when we deform one shape into another, we can slightly stretch or bend it locally, and we want to be invariant to these kind of deformations, or at least approximately invariant. Now, what we've seen before, for example, when we take the grids as example, right? So convolution in the plane, the way that we worked and the way that, for example, convolutional neural networks work. So we have some local filter that we move around our image, and we correlate this filter with the content of the image in different locations. So what allows us to do it is the fact that we can move the filter globally. So we have some global representation of our space and a group that acts globally. So we can move this local representation of the filter anywhere in the image. This is typically not the case in differential geometry. When we have a general manifold, then the way that that our filter will move will depend on the path we go. So if in the plane, it doesn't matter which way I go. On, for example, a sphere, it will matter. And we can also have some exotic cases, such as the non-orientable manifolds, the Möbius surface, in which case I will not only have a different rotation, but I can also have a flip of the coordinates. So I have a reflection. I change the handedness. Instead of left-handed or right-handed system of coordinates, I get the opposite one. So there are several recipes how we can generalize the idea of this local filtering or convolution type of architectures to non-Euclidean domains. So we can, for example, say that we fix a path. So there is a kind of canonical path between two different points. We'll call it the geodesic. So I can go along a certain path. I can fix the gauge. So I can say that I don't have any ambiguity in my system of coordinates because I pre-computed. We'll see that it's in principle possible, but it raises certain difficulties. We can also say that, okay, if I have an ambiguity such as rotation, let's do a form of pooling over all possible rotations. Then if, again, I have ambiguity of rotations, I can say that I have a filter that is isotropic, so it's rotationally invariant, and then it doesn't matter how I rotate the local frame. And finally, and this is what Taco will be describing in his next lecture, we can have a filter that is gauge equivariant. So it will change in the same way as if I change the system of coordinates. Okay, so I will focus mainly on these three possibilities of fixed gauge, group pooling, and isotropic filters. But before that, we'll need to get some background about differential geometry. And basically, we need to discuss three things. So first of all, how to define local stuff on manifolds, right? So what I said that we have a local filter that in the Euclidean case, right, on the grid, we just extract a block of pixels from the image and we multiply them by some mask. So this is significantly more elaborate on a manifold. So we'll need to understand what is a Riemannian metric and, for example, an exponential map in order to do it. Second question is how to move things around. So we'll need to understand about parallel transport, how I move things, for example, how I move a vector on a manifold such that I preserve the angle. And then we'll talk about symmetries and invariances that are related to manifolds. And again, the local version of it will be discussed in the next lecture. So here is a crash course on manifolds. So what are manifolds? So it's good to imagine something like the sphere or maybe this kind of two-dimensional blob. Okay, so these are, technically speaking, are topological spaces. So the difference between topology and geometry roughly is that we have the notion of neighborhood, but you don't have the notion of distance. So I can tell who are my neighbors, but I don't have the notion of how far they are, right? So I don't have the notion of a distance and I don't have the notion of angles. So I don't have inner products. So it is a very basic thing. Basically, topology operates with a concept of open sets. Okay, what is a smooth manifold? Basically, we have smooth transitions between what is called local charts, right? And I have basically a manifold is a topological space that is locally equivalent to the Euclidean space, right? This is what we call homeomorphic. So an S-dimensional manifold is locally homeomorphic to an S-dimensional Euclidean space. And since in most cases we'll be talking about surfaces, so these are two-dimensional manifolds and they are locally topologically equivalent or homeomorphic to a plane. Okay, and this is what we call the tangent space or the tangent plane. You can think of it as attached to every point, and we call the tangent bundle collection of all the tangent spaces. So again, some technical subtlety. So this is what is called the disjoint union. So we consider the same spaces differently if they're attached to different points. Okay, so bottom line, we can represent the manifold, the space around every point, but we don't have a global representation for it, right? So we can work in the tangent space only locally. So in the tangent space, we have tangent vectors. So I denote them by capital letters, X, and they model kind of local displacement, right? So we can then identify them with directional derivatives. What is important to understand about vectors in geometry in general is that they're coordinate free, right? So these are abstract geometric structures. And I don't know how you were taught about vectors, but often you're said that the vector is an arrow, right? You can think of it as a kind of an arrow, or you can think of it as a kind of array of numbers. So both views are incorrect. technically speaking, because vectors are just abstract things. And the only thing that you can do with them, you can add them and you can multiply them by a scalar, and they satisfy a set of rules. So that's how you define a vector space. In order to think of a vector as an arrow, you need an extra notion that is called the inner product. And then you're talking about a space with a vector space with an inner product that is called the Hilbert space, right? So this is what gives you a notion of direction. In order to talk about vectors as an array of numbers, you need coordinates. So you need some basis with respect to which you can represent the vectors. And this is the local basis. So a choice of S, in this case, in this figure, two vectors that are not collinear, so they're linearly independent, and they span the tangent space, and I can represent with respect to these vectors any vector in the tangent space by projecting them on x1 and x2. And this is what we'll call a gauge. So basically the collection of these local bases that depends smoothly on the position. So if I move from point U to a point nearby, this choice of basis vectors will not change abruptly. Okay, so this is just a fancy name used in physics for this collection of local reference frames. And what the gauge allows us to do with the vector is exactly represented as an array of coordinates. So I will denote these the array of coordinates, the coordinate representation of a vector by small bold letter x. Okay, now the fact that we consider so far manifold as a topological object means that it's a kind of very flexible, infinitely flexible rubber object, right? And there's this joke about a topologist's breakfast that you can have coffee from a mug and then deform it continuously into a torus, into a donut, and then eat it, right? So this means that we don't have really any notion of geometry on these objects. So we need to equip our manifold with geometry, and this is done through a notion that is called the Riemannian metric. So Riemannian metric is just a local inner product at every tangent space at every point, right? So it's typically denoted by G, or just inner product with subindex U. And it allows us to locally measure angle, length, and area, right? So the angle is just given as the arccosine of the inner product between two tangent vectors. The length will be just the norm induced by this inner product. And the area, we can measure it as the determinant of this quadratic form G. So I can express it as a matrix with respect to some system of coordinates, and the determinant is coordinate independent. And we call quantities or properties that are expressible entirely in terms of the Riemannian metric intrinsic. So once I have defined a metric on a manifold, then if I do something to this manifold and the metric doesn't change, then everything that is expressed in the metric also, in terms of the metric, also doesn't change. So intrinsic properties are very important because they're invariant to certain types of deformations that we will call isometries. So another important notion is the notion of geodesics. So if I have 2 points on the manifold, let's call them U and V, I can define a curve. So I parameterize it over some interval between 0 and t capital that goes from point U to point V. Okay, and at time t, so think of it as time. So think of it as some kind of car that drives from point U to point V. So at time 0. At the starting, it's at point U, and the time t that has taken to drive there, it gets to point V. Okay, so we assume that the curve is smooth, right? So everything is differentiable. We can talk about the tangent or velocity vector as the derivative of this curve with respect to the parameter t, right? And basically, at every point, it belongs to the tangent space at the relevant point, right? So if I'm now at point t, then the velocity will be a tangent vector in this space in the tangent space at that point. So how can we measure the length of the curve? I can just break it into these small intervals and sum them up, right? So if I take the limit, then we get integral over the length, right, or the norm of the velocity vectors. And I remind you that the norm is given by the Riemannian metric. And if we integrate it between 0 and t, right, with respect to the time parameter, we get the length of the curve. And geodesic is simply a length minimizing curve. So out of all the possible smooth curves that connect 2 points U and V, the one that is the shortest will be the geodesic. So what is important to know about geodesics is that they are intrinsic. So they are defined through the Riemannian metric, right? And you can see it here in the definition. So if I change the manifold in a way that doesn't change the Riemannian metric, you can see from this formula that the length of the curve will not change. Now, given this, we can also define a geodesic distance. So I simply say that the way of measuring the distance between 2 points will be just build a geodesic between them and measure its length. So there is a question about how can we determine the direction of any point on the manifold. So it's not the direction of a point, it's a direction of a vector, right? And the direction is relative. So if I have 2 vectors in the tangent plane, I can measure the angle between them using the Riemannian metric, right? Using my inner product. So that's how it's determined. Okay, but we don't have a global direction. So this is not something that is defined. So the Riemannian metric acts only locally. Okay, so here is a little bit confusing choice of terminology is that distances are often also called metrics, right? So there is a branch of geometry that is called metric geometry that operates with generalization of distances that are called metrics. So in order not to confuse the two terms, because we also called a metric this bilinear quadratic form that the inner product on the manifold. So I will prefer to use the term distance. Okay, so geodesic distance again is a way of measuring the distance between any 2 points on the manifold, and it will be just given as the length of the geodesic connecting them. What is important to understand that not always, in general, as you can assume in mathematics, it doesn't. It's not taken for granted that certain thing exists, right? So when we write a minimum, it doesn't mean that the minimum exists. So you can find examples of spaces where the minimum is never achieved, right? So we can show that if the manifold is connected, then in other words, you cannot represent it as 2 coverings that are disjoint. We can achieve the minimum of a geodesic, and then we call such a metric space complete. So completeness, technically speaking, means that every Cauchy sequence converges, right? And we'll see that in Riemannian geometry, there are several equivalent definitions of completeness. Okay, what is also important to understand that geodesic distances are intrinsic. So again, if I bend the manifold without changing the Riemannian metric, then the geodesic distances will not change. And an important result called the Hopf-Rinow theorem establishes the equivalence between metric completeness, in other words, that every Cauchy sequence converges in this metric space, and geodesic completeness, which means that I can shoot a geodesic from any point in any direction and follow it indefinitely. So I can create a path and follow for it until I'm tired. Now, another thing that geodesics allow us to do is to define what is called the parallel transport. So it's a way of moving a vector from point U to point V, right? So let's say that I have this vector X at point U, right? So it's a tangent vector in the respective tangent space. I can define a geodesic that goes from U to V, right, with these endpoints. And now I can define a family of vectors. I denote them X, T, right? So they are parameterized by this curve, by the geodesic. And I want that along this curve, the length of the vector is constant, right? So that's measured by the Riemannian metric. And then the angle between the vector and the tangent to the curve, the velocity vector, is also constant. So in other words, I'm moving 2 vectors such that the angle between them is preserved. So if this is satisfied, we say that X is parallel transported along the curve. Okay. So there is a question here: why you define the inner product on gamma t instead of t of gamma t? Yeah. So this is just a notation, right? So we said that we define the inner product at some point, right? And it's an inner product on the tangent space at that point. So it's just to say that the inner product that is on the tangent space at that point, and gamma t is a point on the manifold, right? So it's a point on the curve. Okay, so this was just a notation, right? And parallel transport, it is also called a connection. Basically, it's this map between 2 tangent spaces: tangent space at point U and tangent space at point V. And basically, it's a mechanism to transport vectors between tangent spaces. It is also intrinsic, so I can express it in terms of Riemannian metric only. This is how I define it. And it amounts to rotation. On a manifold with a metric, basically what happens to the vector, right? Because we said that the length of the vector is preserved. I have a mechanism to measure it. What happens to the vector is rotation, right? So this map just rotates the vector when I move it from one tangent space to another, right? So it's an element of the special orthogonal group. So I should also say that connection is more general than what I described here. We can define it abstractly without resorting to Riemannian metric through what is called a covariant derivative. So therefore, you can have multiple connections defined on manifolds, but there is a special one that is called the Veličković connection that is torsion-free and compatible with the Riemannian metric. So if I define, basically I can define a connection on a manifold without any Riemannian metric, but if I give you a manifold with a Riemannian metric, a Riemannian manifold, then there is a unique connection that is a special one that is the Veličković connection. So in our case, because we are talking about many Riemannian manifolds, we will be assuming if we are talking about connection, right, or a parallel transport, then it will be this special one. Okay, but allow me not to go into details what is meant by torsion. So another important concept is exponential map, and basically it's a way of mapping locally around point U to the manifold, right? Basically, the way that I can do it is if I have a point U, I can always define a geodesic that starts at point U in some direction, right? So you can give me a vector X, and I can define a curve for which the tangent vector at point 0 will coincide with X. Okay, and I can follow this geodesic, and when this geodesic is defined for any t, right, from 0 to infinity, this is what we call geodesic completeness, right? So I can follow this path indefinitely. And the exponential map is defined by taking a unit step along a geodesic in certain direction, right? So geodesic exponential map takes us from the tangent space. So it takes a unit vector, defines a geodesic in this direction, and takes a unit step along this geodesic, and it lends us to a point on a manifold. Okay, so that's what exponential map does. So basically, what it allows us is it allows us to work on the tangent plane, but to go and to fetch values of something from the manifold, right? As we'll see, this will be very handy when we, for example, want to define a local filter. I will need to use the exponential map to bring the values of a function defined on the manifold, and then now I work in the plane, right, or in the Euclidean space, where it's much more convenient. So before, it is also intrinsic. Now, what the subtle point is that geodesic completeness doesn't guarantee that the exponential map is a global diffeomorphism. In other words, it's a differentiable bijective map with differentiable inverse. So we might have some disasters like is shown here. So if I extend it too much, then it will not be smooth, it will not be differentiable. And the largest radius for which this map is diffeomorphic is called the injectivity radius. So it might be different at every point, and usually injectivity radius of the manifold is the smallest one across all the points. So this is all you need to know about manifolds, about differential geometry. So let's now see how we use it to define something similar to convolution. Okay, so we'll assume that we have some signal on the manifold, right? So it's a function defined at every point. So let's say scalar function. And we define a filter that I denote by psi, like before, in the tangent space. Okay, so conceptually, what will be the analogy of spatial convolution is that I take the integral of the filter, right, and I integrate on the tangent space at every point with the values of the function that I bring to this tangent space through the exponential map. Okay, so I compose here the signal with the exponential map. So it allows me to take a vector in the tangent space, and it will correspond to a value of the function, right? So it gives me a local view on the function around the point U, right? So this is how it looks like. And then I just correlate it with the filter that I define in this space, and I get an analogy of convolution. The problem here, of course, is that these are abstract geometric vectors, right? So I don't really have a way of computing this integral. in order to do it, I need to define a gauge, right? So I need to represent vectors as an array of coordinates so I can deal with them on the computer. And this implies that I need to define a local gauge, so a local system of coordinates. And the problem is that this gauge is arbitrary, right? I can define it in many different ways. So I need to say that the convolution here depends on the choice of the gauge. And if I change the gauge, I will get a different result, right? So if I rotate, for example, my local system of coordinates, then the result of this integration will be different. So the question is, how can this gauge transform, right? So what is our ambiguity? So if we just have a naked manifold, so to say, so just a topological object, then any change of coordinates by an invertible matrix, what is called the general linear group, is allowed, right? So I don't have really any other structure. So what I need to ensure that it's not degenerate. Otherwise, any linear transformation is possible. So any invertible matrix. If I have an orientable manifold, then I can talk about what is called GL+, and these are invertible matrices with positive determinant. If I have a manifold with a volume form, right? So you need to understand that these notions are independent of the metric, right? So you can define a volume form separately from any Riemannian structure. Then we're talking about matrices with determinant equal to 1, right? So determinant can be thought of as a representation of the volume. If I have a manifold with a metric, then I have a notion of direction, right? So we can talk about, we can restrict our ambiguity to orthogonal matrices that preserve directions. Now, orthogonal matrices can still flip the orientation, right? And this is exactly what happens on surfaces such as the Möbius surface, which is not orientable. So if I have manifold that has metric and orientation, I can also restrict these matrices to have determinant 1, right? So they preserve orientation, and we are talking about the special orthogonal group. And finally, if I have a manifold with a frame field, then there is no ambiguity. So this gauge is prescribed exactly. And here you can see a visualization of these ambiguities. So this is rotation ambiguity. I can choose a gauge and I can rotate it arbitrarily at every point. What is important, differently at every point. If I have, for example, the Möbius strip, so it looks like the plane, but the only thing that changes here is that when I move from one point to another, I can flip the system of coordinates. And then when I have a fixed gauge, like on the sphere, for example, we have some canonical way of choosing coordinates, then there is no ambiguity whatsoever. Okay, so in practical situations, we deal with these two settings. So we have either manifold with a frame field, we'll talk about it in a second, or we have the SO3 or SOS or SO2 ambiguity, so local orientation preserving rotations. So here, as I said, we have several possibilities. So we can fix a gauge, we can do group pooling, we can do isotropic filters, and we can do gauge equivariant filters. Okay, so the first thing is, let's try to fix a gauge. So there are actually techniques how to do it. So you can take, for example, an intrinsic function and compute an intrinsic gradient of it. We'll talk about it in a second. And this gives you a set of vectors that are smooth, but they can also be vanish in a few points. So if you are happy with the vectors vanishing at a few points, then this is a valid solution. Okay, and another possibility is to have an angular pooling. So let's say that we use polar coordinates to define our filter in the tangent space, in the tangent plane. So here we can say that I don't know how to orient the filter, so let's look at all the possible orientations and correlate the filter with basically rotated versions of the filter with my function, and then take the maximum, right? So it's kind of correlation with the rotating mask. So of course, this way I throw away some information. We can also have isotropic filters. So isotropic filter means that now the filter is rotationally symmetric, so it depends only on the radius, not on the angle. And in this case, I don't need to do what I had to do previously, right? But I lose discriminative power. So the filter is symmetric. Now let's talk about deformation invariance. And this is what we have achieved so far, right? So we have a filter that is defined intrinsically on the manifold, and if I deform the manifold, then I don't suffer any deformations if this deformation is such that it doesn't change the Riemannian metric, right? So what we will call an isometry. So we can think of domain deformation as a map between two different manifolds, right? So we have a manifold omega, we have another manifold omega wave, and I have a map, let's call it eta, from omega to omega wave, right? Now, what is important to understand is what I need I will need to describe now is how it changes the Riemannian metric, right? And usually you would just say that, okay, if I have a point, I have infinitesimal displacement from this point, I can also make an infinitesimal displacement from the image of the function, right? And this is what is called the differential. So the analogy of this is called the push-forward map. So the analogy of differential in Riemannian geometry is a map between two tangent spaces. Remember that we said that tangent vectors are a model of local displacement. So that's exactly it. So if I'm at point U and I make a displacement by vector x, then I can tell you how this displacement will affect the will be mapped by under the map eta by this function that I call the push forward, right? D eta, that maps me to another tangent space on the manifold omega wave around the point eta u, right? The image of this point under eta, and this tells me how exactly I changed. So I can define the opposite. So I can define the pullback. So the pullback tells me basically how the metric will be affected, and this is called the pullback metric. So I can measure the distances right locally, or I can measure inner products on my original manifold, right, in the tangent space around point U by going to the other manifold, right, by means of eta, taking the metric from there and defining a new metric on my original manifold, right? You see it. So there is a question, do we have a guarantee on manifolds uniformity? Because the way we compute the geodesic shortest curve assumes that transition between all the points is the same. So I'm not sure that I understand this question. So the transition is defined by the Riemannian metric. So any notion of length or direction is defined by the Riemannian metric. And we are assuming that these are differentiable manifolds, so we can make, basically we can write limits, right? So we can take infinitesimal steps. So all is properly defined, right? So, but back to the concept of pullback, I hope you can understand it, right? So this is what is denoted by eta star h. So h is the metric on my second manifold on omega wave. So I take tangent vectors, right? So metric takes a pair of tangent vectors x and y. I map them by the push forward to the other manifold. I take the metric of that other manifold, and this gives me a metric on the original manifold, right? So this is called the metric pullback. And if these two metrics coincide, right? So if the metric that is given by pullback on the new manifold coincides with the original one that I denoted by G, for every point, then we're talking about a map that is an isometry, right? So technically, it's a diffeomorphism between Riemannian manifolds such that the pullback metric is equal to the original one, right? So it's a map that preserves Riemannian metric. So another way of defining isometry in a different sense is I can say that I have two points, U and V. They will be mapped to some other points, eta of U and eta of V, right? I have the geodesic distances that I define, right, on each manifold, so dg and dh. And if these distances are preserved, right, then I can talk about what we will call a metric isometry. Okay, so basically it's a map now between metric spaces, and if this composition is preserved for every pair of points, then we're talking about metric isometry. Okay, so one follows automatically from another, right? So because we define geodesics as intrinsic, so the Riemannian isometry preserves distances. As a result, Riemannian isometries necessarily metric isometries. And there is a theorem in differential geometry that says that on connected manifolds, the two are equivalent, right? So there is a single concept of isometry. So if I preserve Riemannian metric or preserve the geodesic distances, the two are equivalent. Okay, and this allows us to talk about what we didn't discuss. I think we briefly alluded to in Joan's lecture, signal deformation versus domain deformation, right? So I remind you that what we want, for example, when we talked about invariance, we said that if I have a function that operates on signals on some domain, right? If I transform this signal by some group, and the result of the function doesn't change, then we're talking about group invariance, right? So again, the operation here was on signals on a domain. So here we are in a different situation. We have a domain deformation, right? So we have our domain that we deformed from omega, we now went to omega wave, and we want to make sure that the function that is computed now on this new domain, on the signal on the new domain, will be the same, right? So that's exactly what I showed in this slide before, this kind of situation, right? So when I have some filter that is defined on this domain, and you see that the deformation doesn't change the result of this filtering. So that's exactly what I mean by domain deformation. Now, same way as we had some relaxed notion of this, right? So we could say that if I have approximate invariance, we could measure how far this deformation is from a group, and we can bound the change in the value of the function, right? So that was crucial for convolutional neural networks, for example. We can also do something similar for the domain deformation. So, for example, I can say how far am I from an isometry, for example, by measuring the metric distortion. And this way, I can say that my function is approximately isometry invariant. So all these constructions that I described before will be invariant under isometric deformations and approximately invariant under approximate isometries. Okay, any questions so far? Okay, so if there are no questions, let's talk about the spectral approach to manifolds, how to define a Fourier transform. So we talked about Fourier transforms, talking about grids. So let's talk about the generalization of it, right? And this will be related to isotropic filtering. So I remind you that in the Euclidean case, when we define convolution, we modeled it as a circulant matrix that acts on a domain on a grid with periodic boundary conditions. And we've seen that convolutions or circulant matrices commute, and commuting matrices are jointly diagonalizable. In the sense, you can roughly say that they have the same eigenvectors, and then you can pick up one of the convolutions, the shift operator, and compute its eigenvectors that happen to be the discrete Fourier transforms, and you get that convolutions are diagonalized by the Fourier transform. Okay. Now we could pick up here any matrix. So, for example, instead of the shift operator, you could pick up the Laplacian operator. So on a grid, it looks like this, right? So this is second order derivative. Its eigenvectors will also be the DFT, and then again we get the same result. So what we see is that Fourier basis functions, right? So they are Laplacian eigenfunctions. It's also very easy to verify. The one-dimensional Laplacian operator is just second order derivative. So if I take second order derivative of the exponential, I get back the exponential scaled by the frequency squared, right? So this is the eigenvalue and this is the eigenfunction. We can also interpret the Fourier basis as orthogonal basis that minimizes the Dirichlet energy. So Dirichlet energy will be the norm of the gradient of the function. It tells us how smooth the signal is. So you can interpret the Fourier basis as the smoothest orthogonal basis with respect to this function. You can also interpret it as local difference from your neighbors, right? So if you write the discrete version of Laplacian on a grid, right? So it will be the sum of the two neighbors minus twice the neighbor in the middle, right? So if up to normalization, right? If you divide everything by 2, this will be how different you are from the average of your neighbors. So we would like to define something similar on manifolds. And for this purpose, we'll need the notions of differential operators on manifolds. So let's first define a scalar field, right? So scalar field is just a real function that is defined on the manifold. So to every point, I attach some value, right? So think of temperature of some surface, okay? So I will denote this space by calligraphic x of omega r. Okay, what is a vector field? So it's a function that takes us from every point on the manifold to the tangent space, right, or the tangent bundle. So at every point, it assigns a tangent vector at the corresponding tangent space at that point. Okay. What is the point to apply Fourier transform to a manifold? Okay, good question. So we don't apply the Fourier transform to the manifold. We will apply Fourier transforms to signals on manifolds. The point I can already anticipate is that once you do the Fourier decomposition, you can forget about the manifold. You can work with the Fourier coefficients. So that's the power of the Fourier analysis, that you can abstract out completely the underlying domain. Okay, so basically you have a basis in which you can represent signals. Okay, we'll get to it in a second. Okay, so these are vector fields, and you can think of vector fields as a kind of local displacement or flow of things on the manifold, right? So you can think of flow of particles, flow of temperature. Now we can equip these spaces with inner products, right? So again, these are not inner products like we've seen before on tangent vectors. So these are inner products between functions, right? So the way that I do inner product between two scalar functions is just multiply them pointwise and then integrate, okay? And this integral is defined, so I need to define what is du. So du is given by the volume element on the manifold, and usually you can just take it from the Riemannian metric. That will be exactly the determinant of the Riemannian metric that we've seen before. Now, for vector fields, the way that I define the inner product is I take the local inner product using the Riemannian metric, right? For every point, these are tangent vectors at tu, right? And I can take the inner product between them, right? And this is scalar. So then I integrate it on the entire manifold, and I get a number, right? So this is how I take inner products between scalar fields and vector fields. So I will use exactly the same notation, so it will be clear from the context on what kind of data this inner product is applied. Okay, so what is an intrinsic gradient? So if I stand at a point, right, and I have values of a function on the manifold, I am interested in the following question: what is the direction of the steepest increase of the function at point u? Okay, something that we are keenly interested in many applications, right? When, for example, we do some optimization. So we need for this purpose to define a directional derivative, right? So what is a directional derivative? So directional derivative will tell you that if I move in the direction y, what will be the value of the function as a result of this move, right? So it's exactly given by the differential that we defined before, right? So it's a map between two manifolds. The manifold one is omega, the other manifold is r, right? So it's a trivial one. So it tells us how the function will change if I make a displacement in the direction y, right, at every point. So it is a linear functional, right? Now, you need to understand that linear functionals on vectors are what is called dual vectors, right? So it's something that takes a vector and gives you a number, right? And the vector here is y. And the number is how much the function has changed. Again, I remind you that we cannot say x of u plus du, right? Because this u plus du is not defined. So we need to work with these local displacements. With differential is defined slightly more complicated than in the Euclidean space. Okay. Now we know from functional analysis that every dual vector has a representation as a vector. This is called the Riesz representation theorem. So basically, every linear functional on vectors can be written like this as an inner product, right? And the inner product here is the Riemannian metric, because we are talking about vectors in the tangent space, about tangent vectors. So I can write this functional as an inner product of y with something, with another vector. So this vector is called the gradient, right? So that's actually the correct way of thinking of the gradient. So usually you say that the gradient is the vector, basically an array of partial derivatives of function. So this is not correct definition of the gradient. The gradient is a representation of a linear functional that is called the differential that is coordinate dependent, right? So if you write it in a certain system of coordinates, then indeed you can write it as an array of partial derivatives of the function. Okay, but it's an abstract vector. It's an abstract notion. So that's what we call nabla of x at point u, right? Now, what is an intrinsic gradient when we apply it to the vector field at every point? So this will be a vector field, right? So it's an operator that takes us from scalar fields to vector fields. And it tells us what is the steepest increase at every point of this scalar field, okay? So basically I start with a scalar field and I get into a vector field. And at every point it points in the direction of the steepest increase of the scalar field. So the divergence is the opposite. So it's an operator that turns vector fields into scalar fields. And you can think of it as a flow of the field for infinitesimal ball, okay? So how much comes in and how much comes out. And you can also define, right, or you can think of it either as a property or as a definition that these two operators, the divergence and the gradient, are adjoint. Adjoint means that if I take an inner product between the vector field x, right, and here the inner product will be on vector fields, and the gradient of a scalar field x lowercase, then it will be equal to the divergence of the vector field inner product with the scalar field x lowercase, right? And the inner product here is on scalar fields, right? So basically, divergence is the adjoint operator of the gradient, okay? Now we can also define the Laplacian or the Laplace-Beltrami operator, as it's called in differential geometry. So it's an operator that takes scalar fields and spits out scalar fields. You can think of it as a local difference between the function at a point and its average neighborhood value on some infinitesimal ball, right? Now, this is typically not how you are used to the Laplacian, right? So Laplacian, for example, in 2D is the sum of two-dimensional partial derivatives. And what you get automatically from this definition that it should be rotation invariant, right? So it doesn't matter if I rotate the system of coordinates, I will get the same value, right? So this is not obvious from d squared x with respect to du1 squared, right, plus d squared x with respect to du2 squared, right? The second order derivative with respect to both coordinates of the function. So actually prove it that you have this rotational symmetry. It's not difficult. Okay. What else do we know about the Laplace-Beltrami operator is that it's intrinsic and it is self-adjoint. So in other words, it's symmetric. So basically you can write it as inner product of two gradients, right? So inner product, I should say, on on vector fields, which will be equal, right? Because of the adjoint property, I can move the gradient to the right-hand side, right? And it becomes an inner product on scalar fields, and the divergence of the gradient is exactly how we defined the Laplace-Beltrami operator. So this is how it's defined. And because of its self-adjointness, it will have real eigenvalues, which is important. We can regard them as frequencies, the analogy of frequencies in the Fourier transform. So the operator is named after Pierre-Simon Laplace and Eugenio Beltrami. So Beltrami was early Italian differential geometer that generalized this operator to local coordinates in non-Euclidean spaces. Now, the Laplacian is really ubiquitous. You will find it everywhere in physics. And one example where it appears prominently is in heat equations. So heat equations were studied, heat diffusion was studied as early as by Sir Isaac Newton, more than 300 years ago. And he came up with a law that is called the Newton law of cooling that tells you that the rate of change of a temperature of an object is proportional to the difference in the temperatures between the object and its environment, right? So the diffusion equation is a differential version of this law of cooling. So on the left-hand side, x is the temperature, right? So it's a scalar field. On the left-hand side, you have the rate of change, right? So how much it changes instantaneously in time. On the right-hand side, you have the Laplacian, which measures the difference between the temperature at the point and its environment. And the diffusivity coefficient is some proportion coefficient, right? So here is another equation where it appears is the wave equation. So that was formulated by French mathematician D'Alembert. And basically what it tells is that you have you can think of a wave as a system of masses connected by springs, right? So the tiny infinitesimal masses connected by tiny infinitesimal springs. So the acceleration equals to, from Newton's law, we know equals to the force that acts on these masses, right? And the acceleration will be second order derivative, so that will be the displacement of the masses. And the force here is the local elastic force. This is Hooke's law. So again, given by the in this case by one-dimensional Laplacian. So this is what you see. This is where you see the Laplacian appear in mathematical physics. Another experiment that you can do. So I'm not sure you will hear the sound, but basically here is a plate with a thin layer of sand on it, and if you apply vibrations of different frequencies, you see that at some frequencies certain patterns will be forming. So this was an experiment that was first done by a German physicist called Ernst Chladni in the 18th century. And basically he tried to visualize how different instruments sound. Why, for example, a Stradivari violin sounds better than a cheap violin that you buy for $100 in a violin shop. So he put this layer of sand and applied vibrations to the plate, right, to the deck of the violin by passing a bow on it, and he observed and drew these kind of patterns that were forming. Now, at that time, he didn't have a clue why actually this happens. So he made these experimental visualizations, and he actually toured the courts of Europe, and even Napoleon himself was so impressed that he offered a monetary reward for one who would be able to explain why this phenomenon happens. So now, of course, we have an explanation. So if we look at the wave equation that we've seen before, right? So this is what governs the vibrations of the plate. So the way that we solve a wave equation is by separation of variables. So we have a two-dimensional function of position and time, right? So let's say it's one-dimensional rod that vibrates. So I can separate the solution into a product of the spatial part and the temporal part that I know by phi and tau. And if I plug it into the equation, this is what I get, right? So I can rearrange it, and I get the ratio of the derivative of tau over tau and the ratio of the derivative of phi over phi. So this must be equal for every t and u. So it means that it's constant, and let's call this constant lambda. And you see that the spatial part of the solution are Laplacian eigenfunctions, right? So I get the Laplacian of phi equals lambda phi. So this is what is called in physics the Helmholtz equation. And we can interpret the phi's as vibration modes and lambdas the vibration frequencies. So these were exactly the kind of the patterns that you observed in Chladni's experiment. So the zero crossings of the eigenfunctions is where the sand doesn't jump, right? So where it stays fixed. And this is what he observed. It was the zero level set, or the zero crossings of the eigenfunctions of the Laplacian of that domain. And the frequencies at which these patterns were formed are exactly lambdas, the corresponding eigenvalues of this operator. Now we can compute the Laplacian on manifolds in this way, right? So we cannot put sand on for example, on the human shape, right? Because gravity will just let it fall back. But we can do the same experiment computationally, so we can compute these eigenfunctions. And Laplacian operator on a compact manifold has countable eigendecomposition, so the eigenvalues are discrete. And this is how they look like. So the cool and hot colors represent negative and positive values. So the first eigenvector is constant, right? Like the zero frequency, the DC, what is called in Fourier analysis. And then the first eigenvector is called the Fiedler vector. So it tells you the kind of largest variation direction on a manifold. And then as you go into higher frequencies, then the oscillations, right? So how these eigenfunctions change from positive to negative values will increase. What is important is that these eigenfunctions are intrinsic. As a result, they're isometry invariant. So if I bend this human, nothing will change, right? So the eigenfunctions will look the same. And we can define an analogy of the Fourier transform that I can call a manifold Fourier transform by just taking the inner products of my scalar field X with these eigenfunctions. So these eigenfunctions are also scalar fields, right? So these inner products give us the Fourier coefficients, right? Or the Fourier transform. So this is the analogy of Fourier series. And the inverse Fourier transform, because it's an orthogonal basis, we just take these coefficients and we sum up the basis functions with these coefficients, we get back the signal. Okay, so it allows us to decompose scalar fields in some orthogonal basis, and we can work now with the Fourier coefficients. So basically, we forget about the manifold, right? So I work with these numbers with x k hat. I don't know what is omega here. I don't care what is omega here, right? So somebody asked why we need to define the Fourier transform on the manifold, exactly because of this reason. Now I can completely abstract out what is omega, what is the domain on which I define it, as long as I have a way of defining the Laplacian on this domain and perform its eigendecomposition, I can forget now completely about this domain. Now, what you also see that unlike, for example, the two-dimensional Fourier transform, we have only one-dimensional frequency here, lambda, right? So we can order the eigenvalues, for example, in increasing order. We don't have two-dimensional or three-dimensional frequencies. So we don't have a notion of direction, okay? And we can define an analogy of convolution that is typically called spectral convolution by using what is a property of classical Fourier transforms as a definition. So remember that we could define convolution by taking the product, point-wise product or frequency-wise product of the Fourier transforms on a grid. So here we can define our Fourier transform as I take the products of the Fourier coefficients of my signal and my filter, right? And I take these are the new weighting coefficients by which I weight the eigenfunctions, and I sum them up, right? So this weighted combination will give me some signal on the manifold. Okay. So there are several drawbacks. First of all, we've seen that we have a fast way of doing the Fourier transform on grids because we have different types of fast Fourier transforms. So here we don't have these possibilities, so we need to multiply by basically project on the matrix of eigenvectors. That is usually a dense matrix, so it incurs n squared complexity. So another thing that we see is that the filter will not be localized. And the third thing is that the filters will be isotropic, right? Because we don't have a notion of directional frequency. So the filter will look like this, concentric rings, essentially. And we know that it will be isometry invariant, right? So as we change the manifold, deform the manifold isometrically, we expect the coefficients to be the same, right? And the eigenfunctions to be the same. But in practice, it is unstable because we don't really have exact isometries. So even slight changes in the Laplacian when it goes through eigendecomposition will result in significant perturbations of the eigenvectors. And a good visualization is this. So we have a domain, right? So in this case, it's a manifold representing a horse. We have a signal that looks like these blobs. And let's say that I do some kind of filter. So the filter here does some form of edge detection. So I can write it as a spectral filter. So we have some coefficients. These are the Fourier coefficients of the signal x, and these are the eigenvectors. Okay. Now imagine that what I will do is I will deform the domain, and I will use exactly the same coefficients, right, that are denoted by alpha, coefficients of the filter, on the new Fourier coefficients of the signal that will be obtained in this new basis. And you see that the result looks completely differently. So because the deformation of the domain is not an exact isometry, and especially at high frequencies, I will get differently looking eigenvectors, and as a result, I will have two bases that are different, and the Fourier coefficients, so to say, don't speak the same language. So I cannot apply simply the filter from one domain to another domain. So what we can do something different. We can say that I can represent my filter as a kind of transfer function that I apply to the Laplacian operator. And the way to apply a function to an operator is to apply it to its eigenvalues, right? So that's exactly what I do. So now I have the Fourier transform of the signal, and I apply the transfer function to the eigenvalues, and this is my filter. Okay, and it's a one-dimensional function that will look like something like this, right? So it might be a low-pass filter, or maybe a high-pass filter, or maybe some other function, and this way I get something that is stable, right? So you can see here. So this will be this function that is localized around the point on the horse, and you can see that when the horse is deformed, then this function follows the deformation of the surface, so no disasters happen. Now let's write it slightly differently. So I can write the inner product, right? So the inner product is an integral with respect to v of the signal x and the eigenfunction phi k. So I just change the position of the summation and the integration and assume that this is possible, right? So it is possible when I use the right type of integration, Lebesgue integration. I can exchange the infinite summation and the integral. And what I see here is some function that depends on two coordinates, u and v, right? And this is what we call the heat kernel, typically. So it's a kernel that is position dependent, right? So you can think of it as a kind of spatially varying convolutional filter, right? So in convolution, this thing will not depend on the coordinate. It will depend on the second coordinate. It will depend on the difference of the coordinates, right? So on general manifold, we don't have any valid way of defining the notion of difference between u and v. So we have a function of u and v, right? So let's just make a sanity check how it will look like in the Euclidean case. So in the Euclidean case, our basis functions will be just complex exponentials, right? So because they are complex, also in the inner product, we need to conjugate one of them. So that's why one of them will come with plus. And because exponentials are associative, I can write it as exponential of u minus v. So that's where the standard Euclidean case, the convolution is a function of the difference between the 2 points and not of the 2 points, right? So this kernel is the same at every point. Okay. Any questions so far? So if there are no questions, let's talk about discretization. So we talked about so far about surfaces. So the typical way of discretizing them is using meshes. So meshes, you can think of them as a kind of graphs on steroids. So the question is, how do we determine the transfer function? So that's exactly what you learned. So you need to parameterize it in some way. So for example, it can be polynomial. I will talk about it in a second. And the coefficients of these polynomial are the learnable parameters. So can the steepest increase also be interpreted as the steepest decrease for intrinsic gradient? So the steepest decrease is minus the gradient, right? So the opposite direction. So what is the link between convolution and the Fourier transform? So here there is no obvious link between spatial convolution as we defined it before and the convolution that the spectral convolution we defined now. So it only appears when you use isotropic filters. Okay, so we'll talk about it again in a second when we talk about spectral graph convolutional networks. Okay. Any further questions? Okay, so I see that I'm slightly over time, so let me try to rush through the discretization of manifolds. So we discretize them as meshes. So a mesh, basically, it is what is called a simplicial complex. So graphs are simplicial complex. They have simplices of dimension 0, which are nodes, simplices of dimension 1, which are edges. Meshes have also simplices of dimension 1, which are triangles, triangular faces. So this is how they're defined. And in particular, we are interested in what is called manifold meshes. So manifold meshes must be a discrete version of a manifold. So the manifoldness means that each edge is shared by exactly 2 triangular faces, right? And the boundary of all triangles incident of each node forms a single loop. So I cannot have these kind of examples as shown on the right. Okay, so the example of the horse here that is shown is an example of a discrete manifold or a manifold mesh. Okay, so with every point of, with every node in this mesh, I can associate some coordinates in R3. So this is called an embedding. So it's a geometric realization of the manifold. Otherwise, a mesh like a graph is a purely topological object. We can define the discrete metric. So I can measure just using the Euclidean distance, the length of every edge in the mesh, right? And this will be a discrete metric. And anything that is expressible in terms of this discrete metric is called intrinsic. So if I deform the mesh in a way that this length is preserved, then I'm talking about isometric deformations. Okay. Now in practice, meshes appear to be rigid. So any deformation, usually we don't have a continuous deformation that preserves the metric. So that's why it's extremely important to have the notion of approximate isometries in these cases. So what is a discrete Laplacian? So the discrete Laplacian looks like this. So I at every point, I look at my neighbors, right? So I have a node U in the mesh. I have a neighbor V, and I look at the difference between U and V weighted by some coefficients. And you can see that what it tells you is that it's some kind of difference between the node itself and the weighted average of the neighbors, right? So it's exactly the same interpretation as we had before. So it's how different am I from my neighbors. I can write it as an n by n matrix that looks like this. So the matrix D is the degree matrix and W is the weight matrix. So exactly as we've seen in the graph. Okay, and typically it's sparse with order of number of edges, and for meshes usually the number of edges is bounded, the degree of the nodes is bounded, so it's roughly as the number of nodes, the number of non-zeros in this matrix. So there are several ways of defining Laplacian operators on meshes. The most common that is used in computer graphics is what is called the cotangent formula. It goes back to the 40s, and this in discrete differential geometry was introduced by Pinkel and Petar and by Meyer and Schroeder and de Bruin in the late 90s or early 2000s. And basically what it tells, the cotangent formula tells you that the way that you compute these coefficients W will be by averaging the cotangent of the angles that are opposite to the edge UV, right? And you divide by the area element that is formed by this polygon that is constructed upon the barycenters of the triangles around the point U. Okay, so this is how you compute these coefficients. Now it's not obvious from here that it's intrinsic, but you can rewrite it in this way. So you can express the coefficients using the length of the edges, and you can also express the areas of the triangles using Heron semi-perimeter formula. So the bottom line, this is all expressible in terms of the discrete metric, the edge length, and therefore intrinsic. So we can also ignore the faces and discretize the mesh as a graph, right? So I just have my neighbors, I have just the edges, and you can see that here I get more or less the same thing, right? So the Laplacian looks like this. So I have the degree of x, right? If these are just combinatorial Laplacian, and I just have a 1 as the weight of the edge U and V. And we have the sum of the neighbors. So again, so this is a weighted combination. So it's the feature vector of the node, right, multiplied by the degree, minus the sum of the feature vector of the neighbors. So we've seen this already in graph neural networks. So it's a linear local permutation invariant aggregator, right, that operates on the multiset of my neighbors, right, and the feature vector itself. And it produces a node-wise permutation equivariant linear function, right? So if I multiply my coordinates, right, that are arranged into a matrix X by the Laplacian, I will get this linear function that is permutation equivariant. If I permute the rows of this matrix, the results will be permuted as well, right? So it's a particular case of what we've seen in graph neural networks with Petar. Now, spectral CNNs essentially operate like this. So they apply some function to the Laplacian that then operates on some signal defined on the nodes of the mesh or graph. And the precursors of these methods actually come from discrete geometry processing as early as the works of, for example, Gabriel Taubin from the 90s, or the famous work of Zahi Karni and Craig Gottsman from 2000 about spectral mesh compression. And graph signal processing, so a field that emerged in the harmonic analysis community, notably the groups of Pierre van der Geinst and José Moura in the beginning of 2010. Now, the first construction of a spectral graph neural network was done by Joan in 2014 in their iClear paper, where they applied essentially the graph Fourier transform, which is constructed exactly as they did on manifolds. And this was one of the papers that revived the interest in graph neural networks that were defined before, but it suffered from high complexity and stable and instabilities under perturbations. So the question is, why do we need the Laplacian in the case of meshes? So this is a way, so mesh is a discretization of a manifold, right? So I define the Laplacian on a manifold, and I discretize the manifold as a mesh. So the discrete version of the Laplacian or Laplace trimer operator is a mesh Laplacian, which is a special form of a graph Laplacian, right? Where these coefficients are computed according to some function. All of these, both the mesh Laplacian and the graph Laplacian, are special cases of these aggregation that we've seen in graph neural networks. Okay. So in order to deal with this instability that we've seen before with the example of the horse, polynomial spectral filters were proposed. So that was the ChebNet, the work of Michael de Ferrar, Xavier Bresson, and Pierre van der Geinst, that applies polynomial filters to the Laplacian. And some other functions, of course, are possible. So we had a work that we called ChebNet, which uses rational spectral filters, and also some stability results, including the work of a student who now became a professor at the Technion, Ron Levy, with whom I worked, that proved that such filters are stable. So again, let me recap how we do spectral filtering on a graph or on a mesh, right? So it's more or less the same. So on an undirected graph, the graph Laplacian is symmetric matrix that has orthogonal eigendecomposition. So I can take this matrix and decompose into eigenvectors phi that are orthogonal and a diagonal matrix of eigenvalues lambda. Okay, so the graph Fourier transform will be just multiplying by the matrix phi transposed. So phi contains as columns the basis vectors. It incurs n squared complexity. Inverse Fourier transform is multiplication by the inverse matrix, right? The transpose of phi, again n squared complexity. And then spectral convolution will be just a product of the Fourier transform of the filter and the signal. And usually we design the filter in the frequency domain in the Fourier space. So it will be basically a multiplication by phi of the product, right? So the inverse Fourier transform of the product of the Fourier transforms. Now, what ChebNet does is applies a polynomial filter to the graph Laplacian, right? So the graph applying a filter to Laplacian, I remind you, it incurs applying this function to the eigenvalues, and basically what it amounts to is to take the powers of the Laplacian and multiply them by some coefficients that are learnable, right? That we note here by alpha, and sum everything up. So you see that we can avoid explicit eigendecomposition whatsoever, right? I don't really need to compute these phi's, multiply by the phi's. I just need to take the powers of the Laplacian. So what does it take to compute the power of the Laplacian if I have a polynomial of degree r? So I need to multiply by a sparse matrix r times. So it's order of the number of edges, right? Or on the mesh, it will be order of n approximately. It is stable under graph deformations. Again, I mentioned these results. You can look up. So we can show that if the mesh is deformed a little bit, then the result will be stable. And basically, you can see that even though we started as a spectral filter, right, that operates on the eigenvalues of the Laplacian, it boils down to simple local averaging, right? So Laplacian, what it does, as we've seen, it just averages your neighbors. So you apply this averaging several times to the neighbors of the neighbors. So basically, what you get here is the convolutional flavor of a graph neural network. Okay. So that's how we close the loop. So we started with spatial convolutions. Then we said that we have the ambiguity of the local choice of the gauge. So we could use isotropic filters that come from spectral decomposition. And indeed, we see that applying spectral filters, spectral convolution, boils down to isotropic filters in space. So I will stop here. Please let me know if you have any questions, and then with Taco, you will be talking about the more general construction of gauge equivariant filters.